Let's go over notes for 1.3. This is evaluating limits algebraically. Let me just go through some initial rules here. Limit as x approaches c of b is equal to b. So what all this is saying is, let's say we had a function that was just a constant. That constant is going to stay the same y value. Doesn't matter whatever x you are, it's going to hold that y value all the way through. So the limit of that y value is going to remain that y value all the way through. So just imagine a horizontal line. That horizontal line is never going to change its y value all the way through from, doesn't matter where you are. Let's say we had an expression, a limit statement that says the limit of f of x as x approaches c is equal to L. So we've established that this is a true statement, and the limit of a function is equal to L as x approaches c. So once we have this statement, we can multiply both sides by the same constant and still maintain balance on either side. So that's just kind of some algebraic method there, or just algebraic rule there. The first thing that we should do is when we try to evaluate a limit algebraically, because we don't have the graph in front of us and we're not able to see where the graph is approaching, right? We talked about how limit is the approach from both sides. What we're going to do is we're going to just see, maybe we can just do a direct substitution and see if that works, okay? So to find limits for a function, the first thing we should always try is evaluate the argument in the expression. We just plug in that value, okay? If the resulting value is a real number, then the value is the limit, okay? So if we get a real number in return, then that's our answer. There's nothing more that we need to do. If we don't get a real number, then we have some additional steps that we have to follow. But just to start off with easier examples, let's say we had limit of x squared plus 3x as x approaches 2. So whenever you have an expression and you're trying to find a limit, think of it as evaluating a function at a point. All right, so let's say I gave you a function and it was x squared plus 3x. And I asked you, what is f of 2? Right? And if I asked you what f of 2 was, then you would simply replace all the x with 2, and then you would combine those terms and see what that gets you. So we get 2 squared plus 3 times 2 equals 10. So that's our function value. We're going to approach it the same way with limits. We're going to treat every limit expression as just a function, and we're just going to plug in the value, and we just want to know whether we get a real number. So for a, we plug 2 in for the x's, we get 2 squared plus 3 times 2, 4 plus 6 equals 10. 10 is a real number, so that's our limit. There's nothing more that we need to do. Okay. For b, limit as x approaches 2 of 5. 5 is the function. There's no variable to plug in, so that 5 is going to remain 5 all the way through. Doesn't matter what the x value is, so limit is just equal to 5. Right. Part C, we have a function. So same idea, we're just going to plug -1 in for all the x's and see if we get a real number. And we do. -3 minus 2 minus 7 plus 4 is equal to -8. All right, so far we haven't had any issues. There's no distinction right now between finding limit and evaluating a function at a value. Right. Part D, limit of x cosine of x as x approaches pi. So same idea, replace all the x's with pi. And we get pi times cosine of pi. Cosine of pi is just -1. So we just get negative pi. So that's a real number. It's not a right, still it's still a real number, so we're able to keep that as our answer, and the limit exists at negative pi. So the question is, Why is there no distinction for these problems between a limit and a function value? What is it about these expressions that's causing there to be no distinction between the function and limit? Okay, so the answer is that there's something about all these that's common. All these expressions are continuous. All right, and if we talked about how the times when limit and function value are going to be different and um, uh, are going to give us values that are not the same, is when there's a break in the graph. Right, we talked about how with graphing that whenever we have a vertical asymptote, if there's a hole in the graph, if there's a break in the graph, that is when we're going to see a distinction between function value and limits. And so far, we haven't seen that yet. All these are continuous functions, so function value and limit are not going to be distinguishable as of yet, right? Until we come across some breaks in the graph. So what happens if we do come across a break in the graph and we have to find a limit that may exist, but will not, cannot be found just by plugging in? So if we run into a more complex situation where our just plugging in is not going to get us a real number, then here are the steps we're going to follow. Okay, we're always going to evaluate the argument first. That's always going to be our first step because sometimes we just don't know if there's a break in the graph until we've actually tried it. And let's say we plug in our expression into our expression and we don't get a real number, but instead we get this 0 over 0. So if we get 0 over 0, we call that indeterminate form. Okay. So indeterminate form just means that we have to do a little bit more work. Evaluation needs to go a little further. Now, this doesn't mean that the limit does not exist, okay? We are gonna see situations where the limit doesn't exist, but 0 over 0 just means that this problem is still incomplete. It's true that the function value is undefined because there's a hole in the graph. So this does give us some information. This tells us that there's a hole in the graph, but if we want to find the limit, we can still, we can actually find it if we do a little bit more work. Okay, so the function value does not exist. However, the limit does exist. Okay. All right, let me just run through these steps and we can practice these examples. The first thing we try to do is we want to factor, reduce, and simplify. We want to try to find common factors in order to reduce the expression. And then once we have our reduced expression, then we can reevaluate the limits. And then we'll want to confirm that the resulting value is now a real number, now that we've cleaned up a version. We've created a different version so that we can actually find that result. And if that's a real number, then that's our limit. All right, so here's our example. Okay. Limit as x approaches -2 of x squared plus 5x plus 6 over x plus 2. We don't have this graph in front of us, so we always want to start first with direct substitution, right? Let's see what happens if we do direct substitution. So I'm going to plug -2 in for all the x's. So I get -2 squared plus 5 times -2 plus 6 all over -2 plus 2. Okay. The numerator, I get 4 minus 10, which is -6 plus 6, so I get 0 over 0. As we are going to move forward and eventually we're preparing for the AP exam, College Board just does not like equal signs. So I think it's safer that we just use arrows as much as we can, especially if we're in the intermediate steps before the result. Okay, so now we see 0 over 0. We know that there's something wrong here, right? It's not, it doesn't quite give us what we were seeing from before. So this means that there's something, that there's a hole in the graph. Okay, so whenever you see 0 over 0, you know that there's a hole in the graph. And we know that when there's a hole in the graph, the function doesn't exist at that point, but the limit does, right? We saw from previous graphing where if there's a hole in the graph, right? If there's a hole in the graph, the function doesn't exist at that point, but the limit does. So algebraically, we're going to try to figure out where is the approach from both sides of the graph of that point. So this is how we're going to do it. We're going to try to manipulate this expression so that we can actually figure out where that hole is occurring. Okay. So the way we do that is we look for the numerator and we look at the denominator, and we're asking ourselves, what is it that's causing that hole in the graph? What is it that's making that 0 over 0 to pop up? And there's something hidden in this numerator expression, this x squared plus 5x plus 6. We're thinking that maybe there's a common factor that is matching this x plus 2, and those two common factors at -2 is causing the 0 and 0 to show up. So what we can do is we can factor this numerator. So when we factor the numerator, we're going to be able to get a closer look as to maybe what's hiding behind this standard form. So we can go through our factoring steps. Multiplies to be 6, adds up to be 5. So that's 3 and 2. So x plus 3 and x plus 2. So we have the factor form. It's the same. It's equivalent to this numerator here. But now we see something here, right? We see that there's a common factor. And what if we just remove the hole? So if we remove the hole, what we're doing is we're creating kind of a clone version of this original problem. We're kind of creating a version of this expression that doesn't have the hole in it. Okay, so this is kind of a clone version. And the reason why we want this version is because now, if we have this version without the hole in it, we can now reevaluate the limit. And now that the hole has been patched up, we can figure out where that hole is. And wherever that hole is where the limit is going to exist. So if we plug -2 in for x, we get -2 plus 3, which is equal to 1. I do want to kind of give a visual as to, why is it that we're able to go through this process and arrive at where that hole is. So here is what's happening. This original expression looks like this. And obviously we didn't have the graph in front of us, so we couldn't tell where that, what the picture of this was. And algebraically, when we plug -2 in, we're arriving at that hole, and that hole algebraically is not giving us something that we can use. So what we did was we took out the hole, and when we took out the hole, notice that I call it the clone version because it's virtually the same as this, but now the hole has been patched up. But algebraically, this is useful because now that we've created a clone continuous version of this problem, now we can just evaluate this like as if there wasn't a hole there. We're just evaluating that x plus 3. And then when we plug -2 in, we're able to figure out where that hole is. So algebraically, we're kind of manipulating this function so that we can figure out, where that hole is, because that hole is the location of our limits. All right, let's try that with part B. So first thing first, we always want to just evaluate the expression at 1 or at the x value and replace all the x's with that x value and see what we get. So we get 1 squared plus 5 times 1 plus 6 over 1 minus 1. So here we get 12 in the numerator and we get 0 in the denominator. Now notice how this looks a little different from before. 0 over 0 is a hole in the graph. 12 over 0 is something else. Okay, 12 over 0 means that there is a vertical asymptote. And when there's a vertical asymptote, we know that's when the limit doesn't exist, right? We were able to graphically see that from previous lessons, that whenever we see a vertical asymptote, even if both branches are headed towards the infinity, we know infinity is not a real number, so we know that there's no limit. So same idea here. So 12 over 0 indicates that there's a vertical asymptote at x equals 1. And we know that whenever there's a vertical asymptote, that is telling us the limit doesn't exist.